Assalamu alaikum, I'm Dilruba, and in this video we'll be doing the third VLSI lab tutorial, which involves the design of a ring oscillator. So a ring oscillator is basically a device that has odd number of inverters that are connected in series, and the output of each inverter is taken as the input for the next one, and the last output is fed back to the first inverter, thus forming a ring. And the output oscillates between the voltages of either 1 or 0, so hence a ring oscillator. Now in this lab we'll be using the 0.8 micrometer process technology. Now let's begin with starting our microwind software. Okay, now let's save this first. Alright, so first we'll choose our process technology to be 0.8 micrometer. So go to File and then select Foundry. And then choose CMOS 08. So this sets the length of the transistors to be 0.8 micrometer. After this is done, click on Open. Okay, now we'll be designing the first inverter. So we'll need a PMOS and an NMOS. So let's start with PMOS. So go to Edit and then Generate and then choose PMOS device. If you want NMOS, you can choose the NMOS device. The shortcut way is to choose the MOS generator from the palette. And since we're going with PMOS first, so we'll choose PMOS. And we'll change the width accordingly. So in our lab manual, it's given to be 3.2, which is double of the width of the NMOS, which is given to be 1.6. So after this is set, click on Generate Device and place it. Now we'll do the same process for the NMOS. So go to MOS Generator and select NMOS here. Then change the width to half of what we gave before, so 1.6, and then Generate Device. Then align it and place it. Now this is now we connect the drains of the PMOS and the NMOS together. So choose the Stretch Move tool from the menu bar and connect the drains. We'll then connect the gates of the PMOS and NMOS, so do the same as well. Connect them. Alright, so this is our inverter. If you check out the layout that's been given in the lab manual, we'll see that the inverter has been flipped. So we'll follow this and do the same for our inverter here. So in order to flip, go to Edit and then choose Flip and Rotate and select Flip Horizontal. Select the whole inverter and flip it. Alright, now since we're connecting the output of each inverter to the input of the next inverter, we'll be needing a polymetal contact to be placed right here. So in order to do that, go to Palette and choose the first symbol here, which is the contact metal poly, and place it right here. Alright, this is our first inverter, and we'll be needing 4 more inverters like this to complete the ring oscillator. So we can do that by copying this inverter using this Copy Elements tool. Select the whole inverter and paste it. Let's do this 4 times. Okay, now that we have 5 inverters, alright, the end wells, let's have them have a common end well. So let's delete the other end wells right here using the gun shape tool in the menu bar, and then click on the NVELs to be deleted. Then we'll extend using the move tool. We'll extend the first NVEL until it covers the last inverter. Now they have a common NVEL. Now let's connect each of the inverters together using the metal 1 connection. So let's zoom in around here and connect them. So we'll extend the connection here in order to create the feedback loop. So add more connections. Alright, now that this is done, let's add in the voltage supply, the metal for where the voltage supply would be given to. So place it at the top for the PMOS inverter, PMOS transistors, and we'll do the same for our ground as well, where the NMOSs will be connected to, or the pull down network. Alright, now choose the stretch tool again to connect all the sources of the PMOS to our VDD. And we'll do the same for our for the sources of NMOS. Okay. Now, since in order to complete this feedback loop, we'll be needing another metal to connect them. Otherwise, they'll be current distributed here all the way here, and we don't want that. So let's place it, let's connect them. Okay, now since we have two different metal connections here, we'll need a metal 1, metal 2 contact. So let's go back to palette and choose the metal 1, metal 2 contact right here and place it here at their intersection, and do the same for the other side as well. Can increase the width a bit. Okay, so our layout is done. Now we have to assign and set the voltages input and output. So let's start with setting the voltage supply to the PMOS. So choose the VDD supply here from the palette and place it in the top metal bar. Since we'll be connecting the NVEL as well to the VDD plus, choose the VDD supply again and place it on the NVEL. Alright, now we'll do the same to set the ground at the bottom. Choose the ground from the palette and place it here. Now that's been done, we will move on to the next, where we'll set the input, V input, which will use the clock. So add a clock from the palette to the polysilicon right here and place it. Let's change the name to VIN, as that's our input, and you can have it faster or slower. Let's have it slower for this, and then assign. Okay, now all we have left is the output. So choose the I symbol right here, which is the visible node. This represents the output, and place it for our first output. And rename it assign. Let's do the same for rest of the outputs for each generator, inverter. Okay, so all the assignments have been done. Everything has been set. But before we move on to simulating this, we have to check for any design errors. So in order to do so, go to the menu bar and select the design rule checker right here. And you'll see that the distance is less than 5 lambda, so we'll have to increase the distance. Okay, check again, and we have no more errors. So if you have no more errors, we can proceed with the simulation. So let's click on this green play button right here. Alright, so we have the transient characteristics of the ring oscillator here, but it appears to be zoomed in. So let's increase our time scale to zoom it out. Right now it's at 1 nanosecond. Let's increase to, let's say, 5 nanoseconds. And we also want our frequencies to appear as well. So go to the under evaluate, choose frequency, and then select reset. So there we go, we have our transient characteristics of the oscillator. We have to ensure that our ring oscillator is working correctly by checking their outputs and their response to the inputs, their respective inputs. So for the first one, it will respond to the V input that we had given using the clock. So as we can see, when it's 1, the output given out is 0, and when it's 0, the next output is 1. When the next input is 1, the output is 0, and so on. So it's working well. The same goes here. Since this output will respond to the output here, because this is taken now as the input for the next inverter. So this is the input for this, and this as well inverts the input here. Since they're all inverters, we know that the output is opposite of what the input is. So here we can see when it's 0, the output given out is 1, and then when it's 1, it's 0, and so on. The rest two outputs are also working well. They're inverting. And this is it. Also, the numbers that you see here is 1.25 G. This is the frequency, which is 1.25 gigahertz. So this represents the gain in the frequency for this ring oscillator. We'll have to observe the different frequency gains for different process technologies as given in our assignment. So yeah, this is all for our lab 3 tutorial. If you're still unsure of anything, you can message us and we'll try to help you. And that is all for this video. Thank you and good luck with the assignment. Assalamu alaikum.